Oh, good morning, friends. This is Dr. Faizal Ahmed, and I'm going to uh, have a lecture on basic mechanical engineering, that is iron carbon diagram, right? We will be having uh, spec on this iron carbon diagram. This is iron carbon diagram. In this, we will discuss about various phases of iron and carbon which exist in ductile and brittle materials. And this the figure you are seeing as here you can see here is of iron carbon diagram. Sorry for the inconvenience. And here we are using, you can see here on the x-axis that is percentage of carbon, whereas on the y-axis you see here that you see here is y-axis is on y-axis is temperature scale in degree Fahrenheit. You can see here degree Fahrenheit. On my right is temperature scale. On the y-axis is degree centigrade. And as the percentage of carbon increases from 0 to 0.83%, it represents hypoductile steel, and from 0.83 to 2% represent hypoductile steel, whereas rest is cast iron. These are the phases which it is representing about steel and cast iron. And at a very important point or a line exists at 723 degrees centigrade, you can see here, or 133 degree Fahrenheit degrees centigrade. This important line is there. And as and when the percentage increases, the various forms of iron and carbon and various forms of reactions, various action taking place, that is pyrite and ferrite, perlite and cementite and hypoductite, austenite and solid solution of carbon and gamma iron. You can see here on the top as temperature increase from 132 to this. Then we have this alpha, delta and gamma iron, austenite, ferrite. Accordingly, we can change. We can see here. So this is the representation of iron carbon diagram which it has been representing it. So you friends can take a screenshot for the same, and it is a very important question. And as per your RGPV exams or undergraduate exams, this question is always asked: what is iron carbon diagram? What it represents? What are its significance? What are the chemical reactions taking place here? And further, we will represent about the chemical reactions taking place in the further slide, right? Here you can see here iron carbon diagram crystal structure. So pure iron upon heating experiences two changes in crystal structure before it melts. At room temperature, we call a ferrite or a iron as a BCC crystal structure. Ferrite experiences a polymorphic transformation to phase center cubic austenite or iron at now about degree centigrade. This austenite persists at a 1394 degree centigrade, at which temperature the phase center cubic austenite reverts back to BCC phase, known as ferrite, which finally melts at 153 degrees negative. All these changes are apparent along the left vertical axis of the phase diagram. The delta ferrite is virtually the same as alpha ferrite, except for a range of temperature over which each exists. We have this alpha, gamma, and delta iron here. You can see there maximum solubility of a carbon in various single phases are gamma iron, ferrite, alpha iron, delta iron, stable at only high temperature. Then this various percentage you can see here in these boxes: 0.2, 0.1%, 0.025% is ferrite, and alpha iron 0.008% alpha iron. That is room temperature. The solubility exists. The solubility of a carbon varies in different forms of iron. Delta iron, maximum solubility of carbon is 0.1. Gamma is 2.03, maximum solubility that is possible. As far as austenite, that is a phase center cubic. FCC represents phase center cubic. Iron are solute atoms, and they occupy interstellar position in this lattice. In alpha iron, carbon has a limited solid solubility of about 0.008 percentage. That is at room temperature. Then we have these alpha ferrite, austenite, delta ferrite. Whereas this alpha ferrite represent interstitial solid solutions of small amounts of carbon dissolved in a BCC iron. Maximum solubility of carbon is 0.025% at 727 degrees centigrade and 0.08% at room temperature. As far as delta ferrite is concerned, interstitial solutions of carbon in BCC iron, and upon heating we get austenite changes to BCC and gets delta ferrite. So how this formation of various alpha ferrite, delta ferrite, austenite, cementite and these ledogorite is at 727 degrees at various temperatures, various percentage of carbon, and it been changes it represent that perlite has been formed at 0.8% carbon, 7.7 degrees centigrade, and laminar structure of alpha ferrite and cementite very bright in appearance. So these are the characteristics and properties of various types of iron, carbon, and phases like perlite, cementite, ledogorite, and austenite has been formed. Now see, these are the reactions which has been taking place during these phase transformations. Pentactic reactions in the alloy containing 0.18% carbon, the initial crystals of delta solid solution and the whole of a liquid phase is completely transferred to form austenite on cooling at 1490 degrees centigrade. That is uh, liquid iron plus delta, that's cooling on heating get, we get this gamma austenite. And eutectic reaction is allow with the carbon content 4.33%, the liquid is transferred into austenite and cementite on cooling at this 101,147 degrees centigrade. Right, and in the previous slide we have seen that on the right axis of that, on the right on my axis was degree centigrade temperature. This eutectic or tactic of austenite and cementite is known as lead-uberite. This is very important. What do people will ask? What is ledoborite? What is cementite? So these are the definition of ledoborite. Here, tectoid reaction: iron carbon alloy, 0.8% carbon, austenite transfer into ferrite cementite by this reaction. Gamma austenite on cooling or heating, we get alpha plus cementite, and the tectoid of ferrite cementite is known as perlite. So these are the concepts which is being clear. If the carbon percentage is less than 2.14%, the type of alloy comes under the category of steel. If the carbon percentage is greater than 2.14%, then the alloy comes under the category of cast iron. Now this has been demonstrated in a carbon diagram also. Then we have hypoprotectoid steels, hyperprotectoid steels, and protectoid steels. These are the major characteristics, categories of steels which been used there. Steels with carbon content from 0.025% to 0.8% are called hypotetride steels, and with carbon 0.8% non-tetride steel, which can be easily seen in a carbon diagram. Here we see that with tactile steel, the various type of microstructures we can see here under the microscope at a nanoscale or at other magnification point. We can see here these are the microstructures which is existing at various existing, and iron carbon diagram also we can see here at various points. There are solid state transformation in this steel. Hypotetride steels have solid state transformations. They are transformation of gamma iron to alpha iron and decomposition of austenite. The limiting composition for getting perlite is this. With carbon content less than this amount, no perlite can be formed. The alloy will contain only ferrite grains. Steels containing carbon between 0.025 to 0.8% would contain verifying amount of ferrite and perlite, and their relative position depend on the carbon content. So that's all for today. Thanking you.